Hello again, everybody. We're going to go over exam 3, go over version B. So this is the worked example for version B of exam 3. Here's question 1. Give the set of 4 quantum numbers that would represent the last electron added to cobalt. So here we have cobalt. We're in row 4 of the periodic table, so we're going to be adding electrons to the 4s and the 3d subshell. So there's one orbital for 4s that's going to hold potentially 2 electrons, and here's the 5 orbitals for d that are going to potentially hold 10 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons we have to put in here. So we're normally going to go 1, 2, 3, 4, 5, 6, 7, 8, and then this one right here is our 9th, our final electron. So if we look at that, we're the spin down in the second orbital in 3d. So our n is going to be 3 for the third energy level. L would be 2 for d. M sub L, this would be -2, -1, 0, +1, +2. So this is going to be -1, and M sub S, this was our spin down electron, so -1/2. Place the following elements in order of decreasing atomic radius, and we have indium, rubidium, and xenon. If we look at these are all in row 5 of the periodic table. So we're just going to go from left to right for largest to smallest. So rubidium is the farthest over, followed by indium, and then xenon. Choose the paramagnetic species. So for calcium, what we would have is 4s, and that's going to have both electrons there. So that's 4s2, so they're all paired. So that's diamagnetic. O2 minus would have a full 2s subshell, and then normally its 2p subshell would only have 4 electrons, but it's 2 minus, so it's taken on 2 more electrons. So these are all paired. So O2 minus is diamagnetic. For zinc, 2 plus, there we are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we would have 4s2, 3d10, and it's 2 plus, so it's losing 2 electrons, but where it's going to lose them from first is going to be right here. So that's going to look like this now. All the remaining electrons are all paired there in the D subshell, so that's diamagnetic. And then our last one, NB3 plus, there it is going to be 5s2, 4d3, one, two, three. But again, we're going to lose the electrons from the 5s first. That'd be 2 plus. The last electron we'd lose right there. And now you can see this has 2 unpaired electrons, so that's our paramagnetic species. Give the complete electron configuration for K plus. So, there we go. So potassium normally would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. But we have K plus, so it has lost one electron and gone to only core electrons taking on that +1 charge. So the only option there, B. All right. Of the following, which element has the highest second ionization energy? So for this, we're looking for not the first ionization energy, but the second ionization energy, which is going to be, here we go. Hopefully you're seeing the same thing I am. Looks similar to this table. Our first column is first ionization energy, second column, second ionization energy, etc. When we're removing our first electron, we're going to have a trend from the left to the right that first ionization energy increases slightly as we go across from left to right. However, once we've removed all our valence electrons and we start removing our core electrons, we're going to see a sudden jump. So if we only have one valence electron, then to remove a second electron would be a core electron, and that's when we see that sudden jump in energy. If we had two valence electrons, then we would have a small increase from the first to the second ionization energy. But when we go to the third ionization energy, and we are now removing a core electron, we are going to see a large or massive spike. So if we look at which elements we had here, there we go. We have Na, Mg, Al, P. So this has one valence electron, this has two, aluminum has three, phosphorus has five. So for first ionization energy, phosphorus would be the highest. But for second ionization energy, because now we get rid of this, in this case, we'd still have one valence electron. Here we'd have two. Here we'd have four. So now that we're removing a core electron from sodium at the second ionization energy, that's why it's going to be the highest. It's going to see a very large spike at that point. Choose the best Lewis structure for CH2, Cl2. So it's countervalence electrons. We've got 4 from carbon, 1 from each hydrogen, 7 from each chlorine. So we should have 20 electrons that we're working with here within the structure. Let's start with carbon as our central atom. Each hydrogen is only going to be able to form a single bond. It only has one unpaired electron, and actually the chlorine is going to be the same way, where it only has one unpaired electron. So what we're going to do is form a bond here with these unpaired electrons. Could be like this, or I guess in the picture it looks like this. Either way, it doesn't matter, but yeah, you're going to have carbon in the center bonded to the chlorides, the hydrogens, and then the chlorides have 3 non-bonding pairs each, so you're going to represent those with those dots right there. So that should be, for this version, answer B. Which electron transition would result in emitted light with the largest energy? So if this is our nucleus, we have n equal 1, n equal 2, and then n equal 3, 4, etc. Those energies actually are getting closer and closer to each other. So the space between 5 and 4 is smaller than the space between 4 and 3, etc., etc., etc. So we're looking at ideally lower level transitions, like a 2 to a 1 is going to be larger than a 3 to a 2. And also which one gives us the greatest change in energy. So A is n equals 5 going to n equals 4. So that only shifts one energy level. The same for D, which is n equals 2 going to n equals 1. That only shifts one energy level. Now, the difference between 1 and 2 is greater than 5 and 4. So if these were our only options, we'd pick going from 2 to 1. But then we also have a couple that jump 2 energy levels. So right off the bat, they're going to, be the choices. We're going to rule out these two. And here we have these, but again, the energy levels. So from, 1 to 2, we have a big gap. From 2 to 3, smaller. From 3 to 4, even smaller. From 4 to 5, even smaller. So the gap from 3 to 1 is larger than the gap from 4 to 2. So when that electron relaxes and goes from energy level 3 to 1, that's going to be the largest energy. For this one, answer B. Calculate the energy of yellow light emitted by a neon atom with a wavelength of 580 nanometers. Other versions might have had a different wavelength. The equation is going to be the same, though. We want energy, which in this case is equal to hc over lambda. So my h is Planck's constant. C is the speed of light. And we want our wavelength in meters. So 580 nanometers would be 10 to the negative 7 meters, or other versions might be 6.8. And for this one, we get 3.43 times 10 to the negative 19 joules, which is answer choice B for version B. Something else for other versions. Which of the following visible colors of light has the shortest wavelength? So shortest wavelength means highest energy. If you think about the visible region, or usually what I'll do is think, so we're going to go, Roy G. Biv. So high wavelength, low wavelength. We have Roy G. Biv. So I have my red, my green, my blue. And I always think about, how I want to avoid UV or ultraviolet rays. The reason I want to avoid UV light is it's high in energy and can damage my skin. So on this scale, in the visible region, of course, what's going to be just outside the visible region, what's going to be right after violet, what's going to have a slightly shorter wavelength than violet and higher energy would be UV. So if I kind of remember in what order to put these, remembering that UV light is high energy, is damaging, and IR, infrared light, is higher or lower energy, higher wavelength, less damaging, kind of reminds me what order to put that Roy G. Biv scale in. So you'd want violet for this one. No two electrons in an atom can have the same 4 quantum numbers. So, we couldn't have n equals 3 and L equals 2 and M sub L equals plus 2 and M sub S equals plus 1/2. If we put another electron in that orbital, it would have to have at least one of the quantum numbers being different. It'd be spin down instead. It couldn't be the same. And that's the Pauli exclusion principle. Hund's rule is that electrons won't pair until they have to. And the Aufbau principle is the order that we fill from lowest to highest energy, 1s, 2s, 2p, 3s, etc. Which sublevel would L sub 3 equal? So again, our options are always, L is always going to be n minus 1 or 0 to n minus 1. So we'd have the options of 0, 1, 2, and 3. And this is our S subshell. This is P. This is D. And L equal to 3 would be F. Which the following statements is true. We can sometimes know the exact location and speed of an electron. Here we go. That's not true. That violates the Heisenberg uncertainty principle. Here we go. So yeah, we can either know the location and not the speed, or vice versa. The principal quantum number n describes the shape. No, L describes the shape. The principal quantum number n tells us what energy level we're in. The spin quantum number describes the orientation of the spin. That's accurate. M sub s either tells us it's spin up plus 1/2 or spin down minus 1/2. So that's true. The magnetic quantum number describes the size and energy. Nope, that's n that describes the size and energy. So C would be the correct answer there. Give the number of core electrons for titanium. And if we go to our periodic table, titanium is element 22. So it has 4 valence electrons. If we work our way back to the, let's go. If we work our way back to the most, or the closest previous noble gas, that would be our core electrons. Here we go. There's titanium. So it has 1, 2, 3, 4 valence electrons. And then, like I said, go back to the closest previous noble gas in this case, which would be argon. That's 18 electrons. So out of these 22, 4 are valence and 18 are core. What's the maximum number of electrons that all d orbitals in a given shell can hold? That would be 10. So 5 orbitals, each one can hold 2. 5 times 2 is 10. Which of the following represents the Lewis dot structure for chloride? We actually kind of already saw this when we did the CH2Cl2. But if we take just our chloride, 7 valence electrons, we're going to start adding 1, 2, 3. We don't want to pair them until we have to, so I add to those 4 quadrants, 1, 2, 3, 4, but we have 3 left. So I'm going to have to pair that, and that, and that. So we'll have 3 lone pairs and 1 unpaired electron right there. So now we have our an abbreviated electron configuration, which is the electron configuration of identical to krypton, and then beyond that being 5s2, 4d1. So krypton, of course, takes me all the way through row 4 of the periodic table. That would be element 19, and then we're going to add 3 valence electrons to that. Or sorry, not 19, 36. So this should be element 39, and we can see there with yttrium that it's going to, have that same configuration. Rubidium, cerium, that takes us through the 5s, and we put 2 of our 3 valence electrons there, and then the third and final valence electron right there. Each of the following set of quantum numbers will specify an orbital. Choose the one that does not contain an error. So we have n equals 2, L equals 2, M sub L equals minus 1. Well, remember, L is going to be anywhere from 0 to n minus 1. So if n is equal to 2, our available options for L are 0 and 1. So because of that, that one's out. N equals 4, L equals 3, M sub L equals negative 4. N is 4, so possible L's 0, 1, 2, 3. That's okay. L is okay. But for M sub L, possible values are negative L to positive L. So we can go from negative 3, positive 3. We couldn't have a negative 4. So that one's out for that reason. N equals 3, L equals 2, M sub L equals plus 2. Yep, for n is 3, so L could be 0, 1, or 2. That's good. M sub L could be anywhere from negative 2 to plus 2, and it is. So that's our answer choice there. And the other one was n equals 2, L equals 2, M sub L equals 0. Again, because n is 2, L could be 0 or 1. Couldn't be 2. That one's out. Range in order of increasing nuclear charge experienced by their valence electrons. So what we're looking at here, potassium, there we go. Bromine, gallium, They're all in row 4, so they all have the same number of core electrons. So the amount of shielding that they're going to get is identical. But then as we go from left to right, the number of protons are going to increase. So with the same amount of shielding, so essentially, potassium has 19 protons. It has 18 core electrons. Its valence electron is going to experience a net +1 charge. Bromide has 18 core electrons, 7 extra protons, so, or actually more than that, what was it, 35, so 17, so this is going to experience a net nuclear effective charge of 17, and for gallium it would be +13. So in order of increasing nuclear charge experience, it would be K, Ga, Br. Place the following in order of increasing metallic character. Metallic character increases going from right to left on a periodic table, and it increases going from top down. So if we've got rubidium, cesium, potassium, and sodium, if I look, I see those are all in group 1A of the periodic table, and the metallic character is just going to be higher, lower metallic character, lower, greater metallic character. So I'm just going to arrange these from what's the highest in that column down to what's the lowest. Yep, so right there. And then lastly, how much energy would a photon released have if an electron and neon transition from n = 3 to n = 2? So the electrons transitioning from a higher energy to a low are low. It's going to lose energy because of that. It's going to release that energy in the form of a photon. How much energy is that photon going to have? So for this, we're going to use this equation right here. Change in energy for that electron equals -2.18 times 10 to the -18 joules times 1 over our final energy level squared and F squared. So our final energy level is going to be 2 squared minus 1 over our initial energy level, which would be 3 squared. So I've got 1/4 minus 1/9. That's going to give me -2.18 times 10 to the -18 times 0.13889. And when I carry that out, I get -3.03 times 10 to the -19, or I think I wrote 28. So that's how much energy the photon released has, or sorry, that's how much energy the electron loses. So then the energy that the photon would have would be positive of that value. All right, that's everything. The exam looked pretty good. The average, I think, was a 73%. As always, if there's any issues, if you think something got marked incorrect that shouldn't have, please stop by my office hours. We'll pull the Scantron. We'll double check it. If there's an error, we'll correct it in web courses. Otherwise, I'll see you Thursday.